These are the notes for embedded triangles with one pair of parallel sides. So back in the first set of notes we did for similarity and dilation, we talked about the fact that when a figure gets dilated and the lines don't go through the center of dilation, the resulting lines are the other lines are parallel. So in this figure, the center of dilation actually occurs at A. And we can see that the AD being dilated ends up with a line AB, that these lines are they're collinear. They end up being the same line. And the same thing for the side AE, AC. However, the side DE, because it does not go through the center of dilation, it turns out that that line ends up parallel to its dilated corresponding side, BC. So once we have that, we have a bunch of proportions that we can write. The proportion of small triangle to big triangle equals small to big equals small to big. So this is all the small to big, are ones that you've explored in great detail by now. These are the common ones that you have seen. The ones down here, these three, actually have to do with looking at the small triangle to the big triangle. And really, I should say small triangle ratio to big triangle ratio. So these, instead of looking at small to big, we're looking at small to big. The ratio that is the newest one that you really focused on when you're talking about these embedded triangles is looking at the little pieces that get cut by the parallel lines. So looking at that A to D is the same, A to D and A to E is the same as D to B, E to C. That the small pieces are also in proportion to each other. You could also write the ratio of A to D, AD to DB equals AE to EC. Both of these deal with the fact that these parallel lines cut the sides of the triangles in proportion to each other. So now we have one example that we're going to look at. In this example, we have a much bigger triangle because it kind of gives us something interesting to look at. And the first thing I'm going to do is I'm going to mark the things that they have given me. So I'm going to mark that DE is parallel to FG, is parallel to BC. I'm also going to mark that AE has a length of 6, EG has a length of 3, and GC has a length of 2, AD of 4, and BC of 10. They then want me to find DF, FB, DE, and FG. So the first one I'm going to find is DF. So DF sits right here. I'm going to set up the proportion that this piece, AD, over DF is going to equal the same as AE over EF. So I have 4 over DF equals 6 over 3. And I now need to solve this proportion for DF. I can't, if I'm isolating DF, but in order to isolate DF, the first thing I'm going to need to do is to get it out of the denominator. I can't have it there. So I'm going to multiply both sides by DF. That's going to result in 4 equals 6 over 3 times DF. Now, in this case, it's kind of nice it works out because I can simplify 6 over 3. 6 over 3 is 2. And so now to solve for DF, I'm going to divide both sides by 2. So we find that DF equals 2. I am now going to add that into my picture just so that I can see the stuff that I am finding. The second one I'm going to find is FB. FB is right here. Now I'm going to find FB using the same idea that we did in this first problem, but I'm going to use what I just found, the DF. So I'm going to say DF over FB equals 3 over 2. Again, because I have FB in the denominator and I'm trying to isolate FB, I need to get it in the numerator. So I'm going to multiply both sides by FB, which gives me 2 equals 3 over 2 times FB. In this case, I'm not so lucky because my 3 over 2 does not simplify in the same way that my 6 over 3 did. So I'm going to have to then also multiply both sides by 2. That's going to get me 4 equals 3 times FB. And then my last step is going to be to divide by 3. So now we can say that FB equals 4/3. And again, I'm going to add that into my picture, my diagram. The next one I'm going to go for is DE. In this case, I am going to write my ratio so that I don't have what I'm looking for in the denominator. Just to kind of mix it up, we can see that we can write the ratios in many different ways, and that if I can write them with the missing piece in the numerator, I actually have a much easier job. So in this case, I'm going to say DE over. So now I'm no longer looking at the pieces that were cut up by the parallel lines. I'm actually looking at a full leg of the small triangle. So I'm going to need to compare that to a full leg of some other triangle here. In this case, the large triangle is what I have, the full leg at the bottom. That's the value I have. So DE over 10 equals, and I'm going to use AE, so 6, over all the big triangle, so 6 plus 3 plus 2, which is 11. Now, this is going to be quicker to solve than the ones we did before because I don't have to multiply by DE, I have to multiply by 10. So I then get DE equals 60 over 11. And I'm done. Again, I'm going to add that into my picture so that I can see that I have found that piece. The last piece is FG, and I'm going to write something, do this very similar process as I just did for DE. I am going to use FG as my numerator. And again, I'm going to use the big triangle since it has a nice round number of 10, and not the little one because 60 over 11 means I have to work with fractions. So now, though, I'm looking at the medium triangle, FG, which means I need to look at the medium side here, so 9. Over 10 is the big triangle, so the side big triangle, 11. Again, I'm going to multiply both sides by 10, so I get FG equals 90 over 11. And neither of these two fractions can be simplified. 60 is not divisible by 11, neither is 90. So I am now done finding the 4 missing lengths. And just to be clear, I am going to draw a line through here so that you can see that these are actually 4 separate pieces to find the 4 missing lengths.